Hello developers, let's start developing. So we're gonna be taking on the second part of task 23 of 2021's Advent of Code, and that's the last task that I need to do because everything else is done. So if you just watched the first part, you might be aware that I created the world's ugliest code in order to do that, when we have an extremely weird way of representing. Basically, we're representing all the connections. The task is that we have this maze and we need to find the way for it to become this maze. There are some rules how the A's and the B's, the C's and the D's can move, and according to those rules and those prices, basically moving an A is 1 item, moving a B is 10 items, moving a C is 100, moving a D is 1000, and we need to calculate the least energy to actually organize them. Yeah, I made a totally brute force that is gonna try all the legal moves in all the possible scenarios, and that takes a while, but it eventually gives a result. Yeah, so this is a prime candidate for optimization later. But the result is correct. This is the result from the one two five two one. Yep, that's the result from the demo thing, which we are not actually reading from a file, but we're just hard coding it like this. So for the second part, we need to do the same thing, only we need to inject these two lines somehow. So we're gonna do that. We're gonna use the exact same algorithm, only we're gonna somehow embellish everything. So in order to do that, what I'm gonna do is that I will extract the things that are the static, and I will just more or less write everything again, only this time with even more rooms and even more thingies. So this is dependent on part 1, this is dependent on part 1, this is dependent on part 1. Is it? Yeah, it is. It has a list of side rooms, it has some logic, CopyBorrow, execute move is complete. Yeah, so everything is hard coded, so it seems that we're gonna have to basically do the whole thing again. But in order to, so there are two ways, at least two ways to do this. One is to copy and paste this whole thing and just append tools everywhere. So we're gonna have barrel paths too, and so on and so forth. But what I will do is basically use the revealing module pattern or something like that. So I will wrap everything here, or this is a nasty solution, so let's get nastier. I'm gonna put everything inside the part 1 method. So the part 1 method actually defines a bunch of methods and functions and types even. Yep, even types, because those are also dependent. And then just run them. Yep, we have everything here, and then we're defining the occupancy, getting the minimum price, and that's all we have to do. Let's see if this thing runs. And this is great because we can do that because JavaScript is dynamic. we can all, and everything is a value, so of course that we can define a function within another function. Why not? It's a value. So this might be an issue in some other languages, definitely not an issue in JavaScript. This is not the best use of this, as I would say that this is definitely by far the worst code I've written this advent of code, but for part 2 I will just redo it, but redo it some more. And now comes the hard part. So let's start on this. So we're gonna have some more rooms. We're gonna have that many rooms, and then we're gonna have the B's and the C's and the D's, but we're gonna have a A. You know what? One thing that I actually wanted to do, but I didn't, and it's actually kind of logical. I'm gonna define some constants. So this means that I can write A1, A2 with the put the quotes or without the quotes, and it's gonna be just the same. Now I want actually A3 now, because we're gonna have an A3, and of course we're gonna have an A4 as well. But we're not gonna have an A5, we're gonna have a B1. B1, that would have been bad. B2, B3, B4, C1, C2, C3, C4, D1, D2, D3, D4. Yeah, it's getting E1. Fortunately, we don't have that. So we're just gonna have A3 and A4 as, and here we have to use them because we cannot use a variable inside the type, but let's see if this gets us. And this is the task that I will most abuse GitHub Copilot on. And then we have a borrow, and then we have a borrow paths that we are gonna ignore for now. And we have whether it can move. Moving from, if it's empty, return false. If we're moving to a non-empty, return false. The side rooms are not this, the side rooms are, and here we can use A3, A4. Yes, no, B3, B4, and C3, C4, and of course D3, D4. Yeah, this is getting uglier by the minute. Are we moving from a side room? Where are we moving? If we're moving from a side room, oh, this is an optimization, which basically does if we are in the final destination, for example, in this situation, a valid move will be to take this A and move it here. It is a valid move by the rules, but it's not a logical move because that thing is in its final position, the final destination. It doesn't make any sense for it to move. And basically that way we're gonna run through a loop, because we can do that indefinitely. We can take this A and move it here, and then take that A and move it there, and so on and so forth, and we can move it always. So we're gonna check here, and the check is also hard-coded. It says you're in the right move if only if you're in the bottom position, and the bottom position is the 2 position, or if you're in the top position and the bottom position is also your thingy, whatever. So that we are not allowing this B to move up as well, because it only has a B inside of it. So we need to change this, because now this will be a bit more complicated. So I will actually use this. we have 2 const 3 is the third side room, is the fourth side room. So now if we are in the fourth side room, yeah, okay, if are we moving to a side room, is it the correct side room? No, I think that I'm writing in the wrong part of the code. How did I do that? Are we moving from a side room? So we have our side room and our side index. If the side room is not our final destination, so because if it's a different room, that then yeah, we can move out. So for example, if we have a C here, yeah, that C is allowed to move out. But otherwise, if the side index is if the side index is 4, don't allow it to move. 4 as a string because side index is a string. Return false. And now, because we're not allowing it to move from position 2, and if we are moving from if we are not moving from position 2, that means we're moving from position 1. Well, that doesn't hold anymore. So we're gonna have to say, if we're moving from position 3 and position 4 is the same as us, return false. So we're gonna do now some even worse code. If we're moving from position 2 and position 4 and position 3 are the same as us, or if we're moving from position 1 and position 4 and position 3 and position 2 are the same as us, don't allow it to move. So this part of the code won't allow an item to move from the correct side room in the correct scenario. Because if we have a situation when we have a B and there's a C underneath, we want this B to be allowed to move. That is a valid move because we need to move the C away. Are we moving to a side room? Yep. Is it the correct side room? If it's not the correct side room, we cannot move there. Is there a pod in the room? Oh, and there was a rule that if there's a pod in the room, we are not, if it's a bed pod in that room, we are not allowed to move there. So yeah, we need 2, 3, and 4. So if we are moving to position 4, we are always allowed to move to position 4. I mean, if the path is unobstructed, because that means there are no other pods in there. But if we are moving to position 3, then we need to check we can only move to position 3 actually. Here I'm gonna optimize this, because right now let's have such a scenario. Let's see such a scenario. We must have it somewhere. yeah, so a valid move for this D is to move here. But I will claim that that is an invalid move. For a D to move in this scenario, I think we can force that D that this is a valid move and this is not a valid move. So this should not be able to move here if the D will be allowed to move here if and only if there's already a D here. So once this D moves here, then and only then this D is allowed to move here. So yeah, I'm gonna do that. And we didn't have that for the first part. Basically, this part of the code is invalid. So we are allowed to move 3. So if 2 is 3, if we are moving to the third position, we are allowed to move that only if there is a D on the fourth position. So if borrow of 4 is not our pod that we're moving, return false. And now we can just add. So if we need to move to 2, the only way we are allowed to move to 2 is if 4 has the same pod and 3 has the same pod. And in that, if we're moving to 1, yep. If none of them are, we can only move to 1 if and only if all of them are done. So that might be a problem. Actually, no. That will, for example, in this case, that will disallow this C moving here. But that doesn't make any sense. Yeah, why would this C move here? Even if it was a D. So even if it was a D, it would not allow it to move here, but so what? Yeah, so we have an optimization. A little bit less ugly code. We are moving to the corridor. If we are moving to the corridor, we need to avoid the entrances. This is so that we can, this detects whether we are colliding with something else. Because first we are determining all the possible values that we can go, and only after that we're saying, okay, are those paths okay? And that is, I think, a major issue of slowness in the application, because right now this B will calculate that this is a valid move, that this is a valid move. All of these are valid moves. And only then it will say, but is there anything in the way? We can do it the other way around and basically say, first check when we're moving somewhere whether something is in the way. But it works. Copying a borrow, we're gonna copy a borrow, but what is a borrow? Yeah, a borrow is of all these rooms. So I think that we managed to implement can move, we managed to implement CopyBorrow. I did quite a lot of moves, methods. So execute a move, copy the borrow, get the path. Yeah, that this is the same. Is it complete? Well, we will need to change this. A3 needs to be an A, A4 needs to be an A, B3 needs to be a B, B4 needs to be a B, C3 needs to be a C, C4 needs to be a C, D3 needs to be a D, D4 needs to be a D. Getting the next moves. So here we have the rooms. Didn't we define some things like this? in the can move. Yeah, let's use the magic of copy and paste. So these are all the rooms that we have. Get the next moves. So this gets the next valid moves. If we can move them, yeah. So for a given borrow, we are determining all the valid moves. Generate a key and a borrow key. Okay. Move key. Get the minimal price. Get next moves, positive infinity to move key, execute the moves. Seems that that part is totally okay. So we are left with one small change. Yeah, of course we're gonna need to take the actual code of part 1, at line 400 and something. And that's this. That's what part 1 actually does. Call the get min price of occupancy. Oh, we need to define the occupancy as well. And that is the place when we will be actually using our input, because now we have the case that A2 is actually a fixed value, and then where are you? Yeah, it's D. So A2 is always D, A3 is also D, and A4 will be our second input. B2 is D, B3 is D. Yeah, as you can see, this is artificial intelligence, it's not magic. It doesn't get that we have a C and a B, but I'm quite interested what it will say now. Well, let's guess A. Yeah, it just, if you need to do anything, do A. So we have a B and a A, so it has a 50% of hit ratio. And let's see what it will do now. Yeah, it's going with the A's again. But the first one will be an A and the second one will be a C. I will check this once more. So we have a DDCB, DDCB, BAAC, BAAC. Yep, we're good to go. Aside from the small detail that I mentioned. And that is the 200 plus lines of this method. Because here we have something that is actually quite useful. For each start and end, for each from and to, we have a list of the whole path that the thing go, or the whole path through which our pod will go. So that's why we are easily able to determine whether it's occupied or not. So this is what you need to do, through which fields you need to move to get from 0 to C2. You need to go through 1, through 2, through 3, through 4, through 5, through 6, and through C1. So if any of them are occupied, that move is invalid. Sorry, we're continuing on. But this means, and I kinda hard-coded this part. But this means that now I will have to hard code much more, because this kind of increases with the square of the fields. So we had 11 corridor fields plus 8 room field things. So we have to do a 361 connection. And out of those 361 connections, basically everyone, including minus to 121, which were calculated, so to say, automatically, which were the numeric corrections. So we have 240 that we had to more or less type in, and that wasn't fun. And now the situation changes that we have still we have 11 corridor tiles, but we have 16 tiles on the side rooms, and that means that we have 700, 600 of which we will have to hard code. That's not fun. So I'm not gonna do that. Yeah, so what I will do is delete this whole thing and try to implement it some other ways. For one, this is a network. Let's try this. Yeah, we have a room and then we have connections, which is a room array. Let's have it like this. So let's define the nodes. We have a room 0 and we have our connections. This can be a node array, so connections are an empty array, and this will be easy to type. Oh, after 10 it guessed A1. Let's see. Yep. Bravo, bravo. So those are the nodes, and now I can say nodes of 0 and yes, only not that. 0 is connected to node 1, node 1 is connected to 0 and node 2. Yes, 2 is connected to 1 and 3, 3 is connected to 2 and 4, 4, 5, 6, 7, 8, 9, 10. A1 is connected to 10 and A2. Well, no, it's connected to 2 and A2. A2 is A1 and A3, A3 is A2 and A4, and almost correct, A4 is only connected to A3. B1 is connected to 2, 4. B2, B2 is correct, B3 is correct, B4 is correct. C1, and see how this thing learns. I changed 2, I changed 4, I don't have to change 6. Yep, yep, and yep, and yep, and yep, and yep, and D4 is connected to that. I only need to add some few connections because this is actually connected to A1 and this is connected to B1 and this is connected to guess correctly, yep. So it gets it wrong 2 times and then it gets it right. Yeah, so this is the map of connections. And now we can do, and I think I may have typed too much. Let's see this in the console, and yeah, this will actually run anyway because it's in a self-invoking function. Once it will load part 2, it will call part 2, it will get called. Yeah, we're missing something somewhere. Of course, we're not returning an empty string. Yeah. So we have this convoluted thing, but you know what? It kinda tried to explain this to me, but I didn't get it. So we don't actually need this. We can just say equals this. Yep, no A1. 1 and 3 and A1. 2 and 4 and A2. Nope, just 2 and 4. 3 and 5 and B1. Yep, 4 and 6. C1. Six and 8. Because I got that I was about to do mapping of this structure with the nodes into a simpler structure that it will be easier to work with. And yep, not connected to A1. This is 2 and A2, A1 and A2, A2 and A4, only A3. So now we're just representing this as a graph. And if we wanted to be sure, we could make something that will generate this array because it is repeatable and it is, so to say, logical. But yeah, let's type this much in. And we don't need this. And actually, why am I being an idiot? Let's paste one more time. Yeah, this is easier. Well, now you should have learned that 2 is connected to A1, 3 is not connected to anything, you are connected to B1, 4 and 6, C1, 6 and 8, 7 and 9, and D1, 8 and 10, just 9. A1 is 2 and A2, it's gonna get one of these wrong and it's gonna put me in trouble. Yep. So this is much better representation of the same data, not this whole thing, but let's see this thing running. Yep. This is our network, and now we just need to find all the paths through the network. And of course, as I already told you, for this last one I will usually try something on the side, and I will have this. Yeah, and I actually used the to everything approach over there. So we're not gonna return result, we're gonna return all paths, because that's what we have. And I will define some more methods, 2 more to be honest. And I'm calling these borrow nodes. What is room connections to? Oh, it's this. So again, I'm gonna use a somewhat inefficient way to get this. Actually, no, this turned out to be rather efficient. Only it is a bit convoluted. And I think we need to actually, yeah, call that. It will be the same, but let's just do that. Is the type? No, the type is wrong. Let's use that. I think that we could also use all paths, because all paths will actually have the exact same data. But let's try that later. So what we're doing, we're taking all the rooms, we are running a double for each through the rooms. So for each room and every other room, set the result to get the path from that one to that one. And how do we get the path from that one to that one? We are using some kind of cache for this, and we have the current path, where we got so far. And again, I'm using blind searching or brute force. So if they are the same room, then the result is an empty array. If they are next to each other, then the result is an empty array. This means you can always move from one to the other, because they're next to each other. You don't need to check any other rooms. If this value already exists, just return it. And note that once I get this result, I'm setting it into all paths. When I get this result, set it into all paths. If it's already set into all paths, return the value. Otherwise, for each connection, see if the current path already includes that connection. That means that we came from there. Otherwise, a path like from 0 to 2, from 0 to 2, from 0 to 2, from 0 to 1, from 0 to 1, from 0 to 1 would be a valid path. And it is a valid path, but we don't want to repeat any nodes. So that says if the next connection would cause us to repeat, just don't ignore it. Otherwise, get the path from my connection to the target room. And these are all the connections, and this is the current path so far because we're passing the connection by definition. And this returns null sometimes. So if it returns null, that means that we don't have a path. For example, we started here, we went here, then we went here, and we want to go this way. So we cannot go that way without backtracking, and this allows backtracking. So we cannot have a path that goes from here, 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 and then goes back here and goes there. Yeah, that is not a valid path. Yeah, however, yeah, I don't think we need this because this is covered by that. But let's leave it in. So if the path already includes the from, that means if we passed the starting point going to the end point, so that means that we made some kind of a weird loop, and we're ignoring that. Otherwise, the result is the path that we are getting for this connection, including the connection. And since the paths are actually unique, the best path, the correct path is unique, that means that we got it. And all paths of from is, we're setting that to the result that we have. And returning the result. And so null means that if the starting arguments don't make sense. Basically, we're trying to move from this room to this room, but we already passed this room. And that says no go. So that's about it. Let's try if this works. Hint, I've actually tried it on the test input. And it takes some time. This is not the fastest solution because it will again try everything. Yeah, we can always pause it here and we'll come back when it returns with the result. It ran and it ran and it ran and it ran for something about 6 minutes and it came up with the wrong number because the answer that we're looking for is 44169. And I have an idea. I've been looking through this and most likely is because of GitHub Copilot. Yeah, and my overall reliance on it. We have end here. So this means that if we are moving into a room and there is a pod in the room, if we are moving in the second position, we need to check whether there's a pod in the third and on the fourth position. Because if we're moving to the second position, basically that means that the first position is by definition empty. Otherwise the path is blocked and we're not gonna do that. And so we're not gonna move there if there is a bad pod in position 3 and position 4. which means that we are allowed to move there if there is a bad pot in position 3 and a good pot in position 4. We need another operator here, so this is not an AND, this is an OR. From what I've looked through it, it looks like everything else is correct. So yeah, we're fixing that and then starting in again and see you in about 5 minutes. And what do you know? Changing that simple thing, just an AND to an OR, turn this into from a 6-minute run into a 10-second run, and we have the correct answer. 44169. Let's verify that once more. Yep, that's 44169. So let's get our input, which is BCBADADC. BCBADADC. Yeah, that's the real input. This is the example input. And let's have it run. And if it's 10 seconds, usually I think that my input was a bit slower than the input for the initial part. It will take at least 10 seconds for the first part, so I would guess something like 20-ish seconds. Oh, it took 18 seconds for the first part, so at least half a minute for the second part. Oh, it finished in 10 seconds again, and the result is 59.71. Let's check whether I am getting my last star for this year's. Yes, that's the right answer, and you are 1 gold star closer to finding the select key. We have almost all the stars. We just need to get the stars that we are getting for free, but that will be in a separate video. Anyway, let's just run all of the tasks now. Excluding 19. I'm still not running that one because, as I said, that takes 20 minutes. Okay, first part is done. Second part done. Task 25, but that one was also slow. And if you remember, that's the sped up version. So here we are. Here are the results, and here is obviously what videos I need to do next after my grand finale video. So we obviously need to optimize task 23. And we also might want to take a look into task 25. And it goes without saying that we will have to optimize task 19. But we'll cross that bridge when we come to it. And for now, we have a total runtime of 47 seconds plus 20 minutes. Bye for now, that's it. This is the last task from Advent of Code. Hope you had fun. I know I had. Keep developing, and bye for now.